Welcome to the annual Stride Student Poster Competition. I'm Lily Eleftheriadou. I'm a professor of civil engineering at the University of Florida and the director of Stride. As many of you know, we hold this every year at the annual Transportation Research Board meeting in Washington, D.C. during our reception. And despite the COVID pandemic, we wanted to go ahead with the poster competition, which has been one of the highlights of TRB. And we're doing it in this virtual format. The students have done a great job adjusting to this. I'm very much looking forward to the presentations and the Q&A. I want to thank Ines Aviles-Spadoni and Ondine Wells for managing the entire process and running the competition. Great job for both, as always. And I want to thank all of you for attending and enjoy the presentations. Don't forget to vote at the end of the presentations for your favorite one, for the People's Choice Award. And I'm going to turn it now over to Ines to begin the competition.
So, hello everyone. I'm Ines Aviles-Spadoni, the research coordinator for the Stride Center, and thanks to Lily for giving the welcoming remarks to this online event. We have 15 students who will be showcasing their work, and we thank them for submitting their videos. Kamar, Amine, they are as follows. Kamar, Amine from Florida International University, Mahmoud Arafat from Florida International University, JongIn from Georgia Tech, Nishu Choudhary from Georgia Tech, Mitch Fisher from Auburn University, Sam Wu Wangbo from UF's Occupational Therapy, Becca Curiosis from Georgia Tech, Syed Morshed from Florida International University, Lindsay Oluyede from the University of North Carolina at Chapel Hill, Rajiv Saha from FIU, Christian Seidler from the Citadel, Akhilesh Shastri from the University of Florida, Tanya Sultana from the University of Alabama at Birmingham, Dan Shu from Auburn, and Lucas Yu from Georgia Tech. Just a couple of quick housekeeping items. This event is being recorded and will be posted to the Stride Center. The event will be structured as such. We'll begin with a showcase where I will call upon each student to play their 3-minute video. Voting for the People's Choice Award will be opened immediately right after the showcase portion of this event, and we will then begin with a question and answer session. So everyone who has registered for this event should have received a link in their email, so check your email. This email will allow you to vote for the People's Choice Award. You can place your vote anytime during the webinar, especially after during the Q&A session. And Ondine Wells will handle that portion, and she'll let you know when the voting has closed. Both the People's Choice Award and the winners of the first, second, and third place videos will be announced towards the end. The first, second, and third place winners have been evaluated by a panel of judges comprised of the External Advisory Board. And with that, I will call now on the first presenter, which is Kamar, Amine.
Hello, my name is Kamar, Amine, and I'm a PhD student majoring in transportation engineering at Florida International University under the supervision of Dr. Muhammad Hadi. This poster is part of the STRIDE project entitled Utilization of Connectivity and Automation in Support of Transportation Agencies' Decision-Making, which aims at modeling, simulating, and evaluating the benefits of connected, autonomous, and connected automated vehicles. This study that we performed at FIU models the red light violation warning application and evaluates its benefits in terms of reducing red light, running violations, and reducing the respective crashes. Calibration is important in simulation modeling to ensure correct and accurate analysis. However, the stochasticity of real-world traffic behavior poses a big challenge. When approaching a signalized intersection at the onset of the yellow interval, the driver will either decide to stop or press the intersection on yellow, creating a dilemma zone. Driver behavior in this case is characterized by the probability of stopping at the onset of amper interval. This poster summarizes the trajectory-based calibration method for driver behavior in dilemma zone to support the modeling of red light violation warning application and assess its benefits accurately. The default parameters that VSIM uses to estimate the probability of stopping at the onset of amber are alpha, beta 1, and beta 2, as you can see. They are used as shown in the equation that is a function of distance to stop bar and speed of the vehicle at the onset of amber. As for the real-world behavior, we retrieved the equations that represent the real-world probability of stopping also as a function of speed and travel time. After collecting the trajectories of the vehicles in the network from VSIM, we performed a nonlinear programming optimization to reduce the sum squared error between VSIM probability and real-world probability of stopping. The calibrated parameters that reduced the sum squared error from 9.75 to 0.003 are as shown below. Plotting the probability of stopping as a function of time to intersection stop bar helps visualize the results of calibration as shown in the first two graphs. After modeling the application in VSIM through COM, we can clearly see in the third plot in the middle that VSIM by default overestimates the probability of stopping and as a result underestimates the number of red light violations, which is zero before calibration, indicating that not one driver committed a violation, and that is a major misinterpretation of real-world driving conditions. We then implemented a surrogate safety assessment model and evaluated the impact of the warning application also before and after calibration. We can see in the last two plots that an uncalibrated model underestimates the conflicts resulting from red light running as well as the benefits of the warning application. After calibration, we found that the warning reduces the number of violations from 9.6 to 0 vehicles per hour as the utilization rate increases and enhances the safety at signalized intersections by approximately 50% at 100% utilization rate of the application, considering both rear and right angle conflicts as shown in the bottom graphs. The methods developed in this study are recommended for use by analysts and modelers when deciding to assess the impacts of connected vehicle-based safety applications using simulation. Thank you.
Okay, thank you, Amine, for presenting your video. Now we will move on to Mahmoud Arafat from FIU.
Thank you so much, Enes, and good afternoon, everyone. And I would like to say thank you for everybody at Stride Research Center, and special thanks to Enes and Untitled for hosting this and for hosting us every year. I would also like to thank Dr. Lily for hosting this annual competition. I'm going to share my screen. Okay.
Hello, everyone. This is Mahmoud. I am a PhD candidate at Florida International University. I'm pursuing a doctorate degree in transportation engineering, and I'm working on connected vehicles, automated vehicles, and cooperative automated vehicles. I work at Lemon Center for Transportation Research under the supervision of Dr. Muhammad Hadi. Actually, this is my third time to participate in the UFTI Stride competition. I participated before in 2019, in 2020, and I never win. So I hope I win this time. So basically, this poster is part of the Stride project titled Utilization of Connectivity and Automation in Support of Transportation Agencies' Decision Making. So we are working at FIU on this project on collaboration with the University of Florida, Georgia Tech, and NC State University. So the overall goal of this Stride project is to develop a library of simulation models that could be used to estimate the impacts and the implication of CVs and AVs in the transportation network. So this study is part of this project, and we modeled a CV application that's called Stop Sign Gap Assist application. So basically, we know that unsignalized intersections has a lot of crashes, a lot of fatalities. So this CV application is considered a countermeasure of these crashes. So we modeled that application in VSIM, but first we wanted to make sure that our models are calibrated. So as you could really see here on the figure on your left-hand side, this is a real-world gap acceptance distribution. We used that model to calibrate our VSIM model. Then we showed you the capacity results before and after calibration. On the right-hand side, you will see the red line. It shows you the capacity without calibration. The blue line is the capacity with calibration. You could really see how VSIM overestimates the capacity at unsignalized intersection without calibration. Then we simulated the stop sign gap assessed in VSIM using CommScript and Python programming to estimate the benefits of that CV application at unsignalized intersection. As you could really see here in the figure in the middle, the results show that the number of right angle conflicts decreases when the minimum gap time utilized in the stop sign gap assessed increase. However, since you are releasing more vehicles in the unsignalized intersection, you could really improve the capacity, but on the other side, you need to be really very careful with designing the stop sign gap assist gap time parameter, because basically you might trade off the safety. So thank you so much for listening to that presentation, and I hope you enjoyed it. Thank you.
So thank you, Mahmoud, for your video. And it's not.
Thank you.
This is the third time that you participated. All right. So moving on to our next post video, JongIn Bai of Georgia Tech. If you can.
Hello, my name is JongIn Bai. I am a PhD student at Georgia Tech studying civil engineering. My research area focuses on the autonomous vehicle operations in mixed traffic environments. I am working with Dr. Michael Hunter on this project, the impacts of autonomous vehicle targeted aggressive merging behaviors on travel time in mixed traffic environments. The objective of this study is to develop interaction behavior models between human drivers and autonomous vehicles. We believe that the cooperative characteristics of AVs will give a motivation to human drivers to take advantage of the AVs and behave aggressively towards AVs. Through our objective, our goal is to observe the impacts of human drivers' aggressive merging behaviors towards AVs near a freeway exit as shown in Figure 1. Figures 2 and 3 show the two different merge behaviors that we modeled in Sumo. The first merge behavior, the aggressive merge, targets the farthest reachable AV, and the second merge behavior, the zipper merge, targets the follower vehicle of the last merge, which results in vehicles taking turns to merge. The key findings are shown in the most right column. The 3+ show the trajectory plus of the vehicles in the base case and the two merge behavior cases. In the base case, there is no aggressive merging behavior. All merges are controlled by Sumo. The blue lines are the exit vehicles, and the red lines are the aggressive merging vehicles. Two findings that I want to highlight are the slopes of the blue curves after the red curves, indicating the disturbance or the impacts to the speed after the merge. The slopes are becoming flatter as the level of aggressive merge increases. The flatter slope suggests the greater disturbance to speed. The second finding is the reduced finish time of the aggressive merging vehicles, indicated by the orange arrows. The orange arrows shifting to the left suggest that the aggressive merging vehicles saved more travel time as their aggressive behavior levels increased. Our next step is to expand our scope to larger network scenarios under various traffic conditions. Our goal is to develop an analytic tool which allows researchers and practitioners to quickly test the impacts of the human driver's aggressive merging behaviors in the presence of AVs. We believe that our findings and products will provide understandings of what can actually happen in mixed traffic under various conditions. Thank you.
All right, thank you very much, JongIn. Now we will go to Nishu Choudhary from Georgia Tech. If you could play your video, please.
Good afternoon, everyone. I'm Nishu Choudhary. I'm a PhD student from Georgia Tech, and I'll share my presentation shortly.
Nishu Choudhary, a PhD student in Transportation Engineering Department at Georgia Tech. I work under supervision of Dr. Anshuman Gwyn and Dr. Michael Hunter. My research area focuses on incident-related delay analysis, and the current study is about challenges associated with rapid estimation of incident-induced delay. To demonstrate the challenges, we've reviewed three commonly used delay estimation methods, namely queuing theory approach, difference in speed approach, and difference in count approach. For comparison, a WISM model was calibrated to simulate a real-life incident. Calibration of the WISM model can be visualized through the two figures given at the left and bottom. These figures compare the aggregate count and speed from WISM and the actual data at the incident site. Once calibrated, we compare the delay estimates from WISM to the ones calculated using the methods discussed previously. The results of this comparison can be found in the figure at the right-hand side, where we can clearly see that difference in speed and the queuing theory approach underestimates the incident delay, while difference in count approach does comparatively better. For difference in speed method, a plausible reason for underestimation of delay is usage of spot speed and count measurements under the assumption of a homogeneous traffic. While for queuing theory, the underestimation of delay is predominantly a result of the assumption of constant arrival rate. So, as demonstrated by above experiment, delay estimation methods currently in use are not appropriate. Therefore, the study has developed a regression-based predictive model to rapidly obtain delay estimates for incidents with varying characteristics under different base conditions. The model structure can be found in the figure given at right-hand side bottom. The model has a tree-based structure, which is based on residual capacity after incident blockage, volume to capacity ratio, and severity of the incident. In conclusion of the study, I would like to say that the comparative analysis of conventional delay estimation methods within the framework of a simulated case study demonstrates how the violation of the homogeneity assumption inherent to the speed-based methods can cause a severe underestimation of incident delay. Thank you.
All right. Thank you, Nishu. And our next poster is from Auburn, and the presenter is Mitch Fisher. If you could share your screen, please.
Will do. Where'd it go? Oh, there it is. Hi, my name is Mitch Fisher, and I'm a PhD student under Dr. Jeff Lamondia at Auburn University. My main research focus is in the area of long-distance travel behavior and how we can use big data techniques to determine traveler trends as well as better understand survey capture consistencies. Today, I'll be discussing some findings from STRIDE Project C3, Emerging Mobility Services for the Transportation Disadvantaged, which aims to identify needs and viable solutions for disadvantaged populations through deploying emerging mobility services. As a facet of this project, determining how rural individuals currently choose their mode will provide researchers, planners, and policymakers valuable insights into the community. In particular, this poster explores how mobility as a service, or MaaS, currently factors into rural mode choice. Nearly 900,000 trips recorded by the 2017 NHTS were analyzed, with over 190,000 of those being rural-based trips. What became apparent, however, was that the personal vehicle is and remains the king of U.S. travel, making up over 93% of the mode split for rural trips. In comparison, MaaS accounted for only 0.1% of rural trips, only overtaking paratransit as a major mode choice. The urban mode split showed similar results in reinforcing the niche market MaaS currently controls. Sociodemographic and trip characteristics of MaaS trips have many similarities between urban and rural locales. This was mainly seen within household income and trip purpose, with the majority of users making over $50,000 a year and mainly using MaaS for regular home activity trips. It should also be noted that MaaS appeared to be more utilized by individuals making under $20,000 a year in urban compared to rural areas. This could hint at the lack of availability of MaaS to vulnerable rural populations. Generational trends show baby boomers to be the most prominent users of MaaS in rural areas, while millennials, the group most associated with MaaS according to the literature, the prominent users in urban areas. Median trip distances place MaaS usage in the same range as personal vehicle and car sharing trips. Compared to urban trips, these rural trips were generally greater in distance, reflecting the sparseness expected in rural areas. Finally, various socioeconomic and trip factors were compared for their influence on alternative rural mode choices over personal vehicles. Using a discrete multinomial logit model, the table on the far right shows some select variables from the final model. MaaS results are outlined. In terms of MaaS influences, trip distance, purpose, and race were found to have negative effects on choosing MaaS over a personal vehicle, holding all their factors constant and relative to the base alternative. Only household income was found to have a significant positive effect on choosing MaaS, with households reporting an income over $200,000 more likely to use MaaS over a personal vehicle when all the factors are held constant. This complies with previous literature showing that typical MaaS users have higher incomes. Overall, these results suggest MaaS usage in rural areas is vastly limited in market size that has similar sociodemographic trends to urban usage. This research is currently ongoing, but will result in a project report and recommendations for how MaaS can be implemented into rural communities. Thank you for your time.
Thank you, Mitch. And now from U.S. Department of Occupational Therapy, we have Seung-Woo Hwang-bo.
Hello, my name is Seung-Woo Hwang-bo, and I am coming from an occupational therapy background, and I'm currently a PhD student at the University of Florida in the Rehabilitation Science program. I'm not specialized, but I have experience with assistive technology and leadership-focused research studies. Currently, I'm working on 2 research projects funded by STRIDE, Project D2, UF and UAB's Phase 1 demonstration study, older driver experiences with autonomous vehicle technology, and A3, UF and UAB's Phase 2 demonstration study, developing a model to support transportation system decisions, considering the experiences of drivers of all age groups with autonomous vehicle technology. And I'm currently working these 2 projects with my mentor, Dr. Sherilyn Klassen, who's the department chair of the occupational therapy at the University of Florida. So highly automated vehicles, which I would refer to Society of Engineering, Automotive Engineering, SAE, level 4 means without human interaction. So fully automated vehicles is a potential way for older drivers to maintain independent mobility regardless of their driving performance related to age-related decline. However, we don't know whether the older drivers would experience motion and or similar sickness, which plays an important role in adopting this technology. So in our study, we wanted to see if the older drivers experience motion and or similar sickness after exposure to automated vehicles, and see if there are differences by mode, so on-road versus simulator, in age, and or sex. And so interestingly, our findings indicated that the exposure to driving simulator had statistically higher scores of the MSAQ than compared to those exposure to the automated shuttles. And however, age and sex did not show any statistical difference. And interestingly, participants from other studies dropped out. However, in our study, nobody has dropped out, potentially indicating that our study has the potential for older drivers to adopt this technology. So the next step is to compare the drivers across the lifespan and also the population with special needs. And so to conclude, the study results indicate the possibility of utilizing the automated vehicles to verify potential benefits to people with mobility needs. Thank you very much.
Okay, thank you very much, Seung-Woo. And now let's move on to Becca Curiosis from Georgia Tech.
Hello.
My name is Becca Curiosis, and I'm a grad student at Georgia Institute of Technology. I'm working towards my doctorate degree in transportation engineering, focused on shared and active mobility. My advisor is...
I think if you're able to turn your volume up a little bit, Rebecca, and you can restart it, I don't think we're all able to hear very well.
Yeah. Do you see a volume? on there?
My name
Go
is
ahead and
Becca
just replay it and maybe we can each adjust our own volumes.
Oh, yeah, sorry, thanks.
Curiosis, and I'm a grad student at Georgia Institute of Technology. I'm working towards my doctorate degree in transportation engineering, focused on shared and active mobility. My advisor is Dr. Carrie Watkins, who I also worked with on this project. Today, I'm excited to share with you my research examining the impact and analysis of ride comfort in shared modes during the COVID-19 pandemic. This research is just a part of a STRIDE project called Enabling the Shared Transportation Revolution, where we're working to understand and facilitate the sharing dynamic in different transportation modes. The COVID-19 pandemic has dramatically changed the way we use transportation modes, and in particular, shared mobility. Stay-at-home orders, social distancing policies, and suspension of services have been implemented to slow the transmission of the virus. For example, shared ride-hailing services have been suspended nationwide since March. These changes to travel behavior may have long-term effects. In order to gain an insight on the impacts of COVID-19 on shared mobility, we developed an online stated and revealed preference survey to measure the comfort and actual usage of the users on shared mobility, specifically private ride-hailing, shared ride-hailing, and public transit, during the periods before, during, and when a vaccine was available for the COVID-19 pandemic. As Georgia was one of the first U.S. states to reopen, the Atlanta metro area provides a useful sample population to provide insight into the future. As seen in the figure of the timeline of the COVID-19 responses in Atlanta, data collection occurred in October and November as the city was fairly adjusted to a new normal. A mixed sampling approach from online methods resulted in 787 survey responses. Although 5 online recruitment methods were used, half of the responses were from a paid online panel service, as it was the most fruitful method. The collection process resulted in a rich set of data. We asked respondents to agree or disagree on a Likert scale to statements to assess their level of comfort using shared mobility. Although a majority of respondents indicated that they felt comfortable using transit ride-hailing and shared ride-hailing before the pandemic, they did not indicate the same level in the future when a vaccine is available. In addition to their stated comfort, we collected their actual usage of transportation modes before and during the pandemic. The largest decrease was in the usage of MARTA rail and private ride-hailing, while the largest increase in usage was in walking and private vehicles. To understand the change in comfort due to the pandemic, we used the usage results and level of shared comfort results to generate linear regression models. Analyzing these models, we found that in the future, comfort levels associated with using shared mobility are expected to increase but not completely return to previous levels. And looking to the future, we're excited to dive deeper into the data and examine shared mobility in a new normal post-pandemic world.
Thank you very much, Becca. Let's move on now to Syed Anaf Morshed from FIU.
Hello everyone, I am Syed Anaf Morshed, a PhD candidate majoring in transportation engineering at Florida International University. The STRIDE project that I'm working on is called Technology Influence on Travel Demand and Behaviors. The lead PI of this project is Dr. Virginia Pico from University of Alabama, and my advisor name is Dr. Muhammad Hadi. This project aims to reduce network congestion by planning transportation network companies and public transit as a unified ecosystem which complies with the STRIDE theme of mitigating network congestion. My poster is called Comparative Mode Split Analysis between Multi-Agent Simulation and Activity-Based Demand Model in the Miami Beach region. In this study, we are using MaaS, a multi-agent simulation tool which is designed to model large-scale scenarios using queue-based approach. The advantage of microscopic agent-based simulation is the behavioral realism of the agents in response to time-varying network changes. The purpose of this study is to develop a method to determine the mode split between the passenger cars and transit services using multi-agent simulation based on regional mode split behavioral model, and to perform our comparative analysis with the results based on the regional activity-based demand model. The main challenges that we face during this research is the calibration of the traffic model based on real-world data in terms of traffic flow and model split. Initially, we had transformed activity schedules into agents plan and used that as an input for MaaS. After running MaaS, we have obtained individual link volume, full day agents plan, and finally modal split of the agents. Then we have performed a parametric calibration for traffic flow and nonlinear optimization for modal split of our model and achieved results close to the real world data. Traffic flow calibration was performed in terms of mean relative error, which was obtained at an acceptable range. And finally, we have introduced different scenarios such as inclusion of metro rail in MacArthur Causeway and road pricing in the model, and observed change of modal split due to dynamic changes within the network. This study demonstrated the effects on mode choice with multi-agent simulation for decision makers according to individual behaviors and trip movements in the Miami Beach region. The calibrated Miami Beach network in terms of the traffic flow and modal split can answer different research questions on transport policies and interventions, for example, public transport reforms, road pricing, emission modeling, to obtain accessibility measures to solve location problems or to develop business ideas based on simulated mobility of the individuals. Thank you, everyone.
Great, thank you, Syed, for your video. And now moving on to Lindsay Oluyede. Lindsay comes to us from the University of North Carolina at Chapel Hill.
Thank you. Good afternoon, everyone. Hello, I'm Lindsay Oluyede, a PhD candidate in the Department of City and Regional Planning at the University of North Carolina at Chapel Hill. My specialization is transportation decision-making, and the title of my research project is Addressing Transportation Barriers to Healthcare During the COVID-19 Pandemic, Perspectives of Care Coordinators. As part of the research team, I worked on this project with my faculty advisor, Dr. Noreen McDonald. We are in the midst of a global health pandemic, which at its onset brought sudden and drastic changes to daily life. Transportation options were reduced or eliminated altogether, and health systems made changes that impacted access to healthcare. This research was conducted to capture the perspectives of social workers, nurses, and other care coordinators who observed firsthand transportation barriers to healthcare access during the pandemic, and how patients, transportation services, and medical providers were able to manage these obstacles. Specifically, the goals of the project were to identify the transportation barriers to care that patients have encountered during the pandemic, innovative solutions medical systems have used to address these access challenges, and differential impacts of these shifts on the groups traditionally most impacted by transportation barriers. Our findings indicate that the pandemic exacerbated existing transportation barriers to accessing healthcare, as well as created new challenges. Yet, there was a silver lining in that telehealth emerged as a critical solution during this pandemic, though it has its limitations. This research uses the term telehealth broadly to include telemedicine appointments with physicians and also non-physician services. So these virtual visits enabled remote access for patients to a broad range of healthcare services, thereby bypassing the need for transportation during an especially precarious time. While the rapid expansion of telehealth during the pandemic was enabled by temporary policy changes, there have been efforts to permanently codify some of these telehealth advances. Insights from care coordinators in this study provide an understanding of how post-pandemic telehealth policy changes could benefit individuals facing transportation barriers to accessing healthcare. Specifically, policy changes that remove geographic and location requirements for patients and providers, widen the range of services eligible for telehealth appointments, and allow for telephone use when internet-enabled devices are not possible, could help make telehealth a more viable solution that supports more accommodating and convenient healthcare for patients and their families.
Thank you very much, Lindsay, for your video. And now we're going to move on to Rahib Saha from FIU.
Thank you, Ines. Good afternoon, everyone. I'm sharing my screen now. I can't share my screen. It's host disabled my screen. So can you give me the authorization?
Let's see. think you're able to share your screen. Let me see, Ondine.
It says host. Yeah, I
Try it now.
I think you should have
Yeah,
received
now it's working. Yes.
co-host privileges. Okay, great.
Hi, this is Radip Shah, a PhD candidate at Florida International University and expected to graduate in April 2021. I am working in ITS lab under the supervision of Dr. Mohammad Hadi. My research interest includes traffic operations, intelligent transportation systems, traffic control design, machine learning, and data analytics. Today, I'm going to talk about an integrated approach for optimizing traffic management plan during freeway incident. Integrated corridor management is a successful traffic management strategy that saves more than 700,000 person-hours of travel time per year. Coordinated freeway and arterial operations, an integral part of this integrated corridor management, improves the mobility of the network by mitigating the congestions induced by the non-recurrent events such as incidents. Although the method has lots of benefits, however, the existing methods and the models of the coordinated freeway operations has some issues, such as the existing models and the methodology are reactive systems, and because it considers some fixed routes for the diversion. On the other hand, to implement the existing methods, agency needs to run real-time simulations. That many agencies doesn't have the resources to implement this system in real time. The third issue is related to the traffic control system. There are two types of traffic control system is commonly available right now. One is the time of day plan-based system, which cannot respond to the variation of the traffic such as the demand surge caused by the diversion. On the other hand, a small number of intersections have the adaptive traffic control system. However, the performance of that system still needs to be evaluated when there is a demand surge or the long queue. To resolve all these issues, we are proposing a new methodology that integrates basically three different methods. One is the machine learning technique, the multi-resolution modeling, and multi-objective optimization. All three methods together creates a proactive approach that resolves all the existing issues. At the same time, the method is easily implementable within the existing framework of the agency. Using this method, we run a case study in Broward County of Florida, and this method gives three types of benefits. The economic benefits, which basically it reduces the average delay and increase overall throughput during the incident in the freeway. At the same time, it also gives environmental benefit by saving fuel and reducing the emissions. And thirdly, it gives us safety benefit by reducing the secondary crashes in the freeway. Thank you.
Hey, thank you. Thank you very much, Rajib. Moving on to the Citadel, Christian Seidler. Let's see, is Christian on?
Ines, I don't see him on. So
He's
is
not
it
on.
possible you play?
Okay,
him?
we can just move on, and if he pops in, we'll come back to him. So from the University of Florida, Akhilesh Shastri.
Hello, everyone. Thank you. Hello, everyone. My name is Akhilesh Shastri. I am a master's student at the University of Florida, Gainesville. I'm majoring in transportation engineering, and my advisor is Dr. Scott Washburn. The topic of my project is providing guidance for selection of interchange design to accommodate ramp metering system. The majority of the existing research regarding ramp metering has largely been focused on ramp signal timing algorithms and or the design of the on-ramp itself, irrespective of the overall interchange design considerations. However, what is generally lacking is a research that considers how ramp metering should factor into the selection of an overall interchange configuration. And this research addresses that very question. The objective of this research was to develop guidance on interchange design with consideration of ramp metering that is appropriate for planning and preliminary engineering level. In other words, guidance is provided to help understand the impact of ramp metering on interchange operations across a variety of interchange designs. Types of the interchanges that were used for this study are the diverging diamond interchange, diamond, spooey, partial cloverleaf, and full cloverleaf. During peak travel periods, when ramp metering is activated, the metering rate or the on-ramp output is typically lower than the on-ramp demand. This results in queue backup onto the adjacent arterial, and that is an undesirable situation from an operational as well as the safety point of view. To avoid this issue, what modern ramp metering systems do is they employ an advanced and sometimes an intermediate queue detectors. So these detectors basically act as pressure relief valves for the on-ramp by increasing the ramp metering output when queue backup approaches the arterial. This may create negative implications for freeway operations. The queue storage distance also plays an important role in the overall operations, so does the arrival patterns. So based on these factors, the recommended interchange design types that would function in a best possible manner in tandem with ramp metering were the diverging diamond, spooey, partial cloverleaf, and full cloverleaf. DDI was found to be the best among all the other forms, striking a good balance between right-of-way footprint and accommodating a wide variety of traffic characteristics. An open source macroscopic queuing analysis tool was also developed as a part of the study. So it served reasonably well as a first cut planning and preliminary engineering assessment tool, and could help identify the inputs that might lead to unacceptable operational conditions. This research helps authorities in the decision of an appropriate interchange type with ramp metering considered together. Thank you.
Okay, thank you very much, Akhilesh. Next up is Tanya Sultana from the University of Alabama at Birmingham.
Hi, I am Tanya Sultana. I am graduating this semester with Masters in Civil Engineering from the University of Alabama at Birmingham, and my specialization is in public transportation and congestion. Under the supervision of my advisor, Dr. Virginia Ciccio Pico, I have been involved in 2 STRIDE projects throughout my study. This poster is part of the project named Mitigating Network Congestion by Integrating Transportation Network Companies and Urban Transit. This part aimed to investigate the utility of public transit in improving network performance and in turn justify the investment for public transit in medium-sized cities. The motivation behind this goal was to discover the potential of public transit to mitigate the congestion produced due to the combined effect of convenience of car use and low-quality public transit. Birmingham was used as a case study, and 3 different scenarios with 1, 5, and 10% public transit were simulated to represent the effect of increased public transit. With the increased transit ridership, improvement in traffic performance is expected in terms of reduction of traffic volume, increase of speed, as well as reduced travel time. The study results showed that throughout the network, the highest volume reduction was 36.6%, highest speed increase was 22%, and travel time reduction was 40.7% after increasing the public transit ridership. Graphical representation of the results for some of the roadway section in 5 peak periods are demonstrated here in the middle column. Also, the visualization of live simulation presented here by green-colored network figure in the rightmost column shows fewer red dots in the right-hand side figure with 10% public transit than the left-hand side figure with 1% public transit, which indicates congestion is reduced with more public transit ridership. Overall, increased public transit reduces congestion by increasing speed and reducing travel time. Thus, it can be concluded that public transit has potential to improve overall network performance in Birmingham or other medium-sized cities. Therefore, while transportation planners and decision makers will think of attracting users towards public transit, the potential utility deduced from this study may encourage them to extend or improve the existing public transit. Thus, this result will help them to justify the investment for public transit. Thank you.
Thank you, Tanya. Dan Shu from.
Hi, thank you for having me, and thanks Stride for sponsoring this project. Hi, this is Dan from Auburn University. I'm a PhD student specialized in transportation engineering. The project I'm currently working on is I3, Evaluation of Work Zone Mobility by Utilizing Naturalistic Driving Study Data, Phase 2. This project is under the guidance of Dr. Hugo Zhou, and today I'm presenting a part of this project, analysis of headway and speed based on driver characteristics and work zone configurations using naturalistic driving study data. In the last phase, we utilized the Sharp2 NDS data to evaluate capacity, car following characteristics, and driver types in 3 freeway work zone configurations. We found that when compared with traditional field data collection techniques, the Sharp2 NDS data offers a unique opportunity to observe actual work zone layout, traffic conditions, and driver performance while negotiating freeway work zones. Meanwhile, very few work zone studies in the past considered driver characteristics and their car following behaviors. But the NDS data can provide this unique information that could not be obtained from field data collection or simulation models in the past. Due to the limited sample size, the first phase recommended collecting more complete NDS work zone trip data that traverse the entire work zone for further study. So in this study, the objectives were set to, firstly, develop time headway selection tables based on different driver characteristics such as gender, age group, and risk perceptions at 4 work zone configurations. And secondly, compare the headway distributions at different work zone consecutive sections. And lastly, perform a speed analysis to explore the speed distribution and speed change at work zones. We selected 200 work zone trips driven by 103 unique drivers from 4 work zone configurations, 2 lane closures, and 2 shoulder closures. The work zone was divided into 6 consecutive sections: 500 feet upstream, advanced warning area, transition area, activity area, termination area, and 500 feet downstream to perform headway distribution and speed analysis by generalized additive model and change point detection technique. The headway selection table based on driver characteristics and their speed profile traversing the entire work zone firstly can be used to enhance work zone planning and simulation models by selecting proper time, headway, and speed distributions based on local driver types. Secondly, develop connected vehicle car following parameters, as the NDS data provides a small moving segment of a lead vehicle and participant vehicle. And lastly, categorize automated vehicle adaptive cruise control for different driver types. All right, this is the end of my presentation. Thank you for listening.
Thank you very much, Dan. Lucas Yu from Georgia Tech is our next and final presenter.
Hi, my name is Lucas Yu, and today I'm presenting on behalf of CB Panor and myself. Both CB and I are PhD students advised by Dr. James Tsai here at Georgia Tech. And the topic I'm presenting today is the AI-based work zone traffic and the driver behavior extraction system using 2D camera images. This research was conducted because work zone as a necessary evil creates congestions and dangerous conditions for the drivers as well as construction workers. And there is a need to obtain real-world work zone traffic data that can be used for traffic studies as well as calibrating and validating traffic simulation models. Such information could include traffic count, speed, time headway, merge location and timing, and many others. Such studies are previously not possible due to lack of extensive real-world data, but widely available traffic cameras in recent years provide opportunities for extracting the necessary data. Thus, we developed an AI-based system that can extract this information from 2D traffic videos. Through our literature review, we identified techniques we can use in our system, as well as common error-causing factors and methods to address them. This preliminary version of the AI systems developed use YOLO deep learning models to detect vehicles from a traffic video and use user-provided labels shown in the center of the slide to help extract traffic count, traffic speed, and traffic merge locations. In addition, we conducted a case study using a 30-minute-long work zone traffic videos collected on I-95. Through our case study, we demonstrated the AI system can extract these data in conditions with different traffic densities. And our initial findings show that the extracted data is promising to analyze driver merge behaviors and gather insights to understand the impact of different traffic conditions. Potentially, these data can help establish optimal traffic control strategies and improve accuracy and reliability of the traffic simulations at work zones. In conclusion, this preliminary version of the AI system opens opportunities for traffic studies to use diverse real-world data, and the system can be implemented in widely available traffic cameras to support transportation agencies' operation. And with further validation and refinement, we believe we can improve the accuracies and reliability of the system even further. Thank you for watching, and have a good day.
Thank you very much, Lucas. And thank you very much to all the students who have presented their video posters. This concludes the showcase portion of this event. And now I will turn it over to my colleague, Ondine Wells.
Great, thank you everybody for presenting today. We're now opening everything up for Q&A. If you have a question, we ask you to please enter it using the chat box. Then I'll read out questions, and the presenter who is able to answer that question will answer it. If you have a specific question, please indicate which project it was for or which presenter, so that will help us out. In the meantime, you should all have received an email with a link to your ballot for the People's Choice Award. So if you, while we're waiting for questions and answers, if you want to go ahead, if you haven't already, go ahead and take a look at your email and you can vote for the People's Choice Award. We're going to leave the Q&A box open for a few minutes so we can wait for questions. So if you do have a question, please contribute that to the chat box. It'll come directly to me. Okay, great. So we have our first question. This is directed to Lindsay. Can you talk about the equity implications of your work? It seems to me that many of the people having trouble with access to healthcare would also not have internet access for telehealth. And you're muted right now, Lindsay, so if you can unmute yourself.
Sure. Yes, thank you for that question. It's a good one. There are certainly equity implications. And so what we learned from the respondents is due to some of these temporary policy changes to expand the use of telehealth, restrictions on devices that require internet connection or that require both an audio and a visual component were waived. And so patients were able to just use a telephone, like a landline telephone, to participate in a telehealth appointment if necessary. And so that is one of our recommendations for post-pandemic policy changes, is to take those types of things into consideration. Just more broadly, all of our respondents work and deal with patients in North Carolina. And from what we heard from those respondents, the majority of the patients that they work with do at least have access to a smartphone. And so even if a desktop or a laptop or tablet isn't available, patients do seem to have smartphone access, which enables them to participate, to utilize telehealth as well. Thank you.
Thank you so much. Okay, we have another question. This one is directed to Saeed Morshed. Is the model capable of taking into consideration variables on people mode choices due to the pandemic?
Oh, that's a very interesting question.
MathSim is a very it's a very detailed software. So I would like to know what kind of parameters in terms of pandemic is the like some who's asking the question, and what kind of parameters are you talking about?
So I don't have a specific answer to those questions, but if you can try to answer generally, and then if that person replies with some more specifics, I'll let you know.
Okay, so basically for mode choice, we have different behavioral parameters that we can insert in MathSim. Since it gives a full day length plan, we can collect some information or through surveys and try to accommodate them to see the change in mode split behavior due to change in those parameters. Thank you.
Okay, super. We have great. The person who submitted that question said that you answered it. Great. Thank you. Okay, question for Becca. Can you expand about the survey methods that you used for your study? It looks like you had 5 different methods.
Yeah, so we had 5 different methods we were trying to implement and put out a survey as quickly as possible to capture all the changing aspects of the pandemic. And we wanted to do it online. So I think the biggest one that we got the most results from was just a Qualtrics online paid service. And we just submit our survey there and they find all of the respondents that we need, and we just set a certain amount. We also tried Facebook advertisements. And so we targeted people in Atlanta, and there was a link to the survey. And that we got some around 100 results there. We also tried to use Mechanical Turk, which is a platform for people to use on Amazon. And it didn't really work at all because that's nationwide. And so just trying to get people in Atlanta to fill out the survey was pretty hard. We also submitted it to people who responded to a survey that Carrie had put out previously, and we got a lot of people responding that way. And then we also sent out emails to different neighborhood groups to put in their newsletters. So yeah, if you have any more questions, let me know.
Great, thank you very much. I'm just checking to see if we have any more questions. I don't see any more. Okay, here, let's see. Okay, this person's not sure which student it is, so if you can all listen and see if this replies to you. It was the project about transit by UAB. Okay, so it's a UAB student. Did you look into any cost benefit implications of the work? How much would it cost to put into place all of the transit improvements you suggest to get to the 10%?
Thank you very much for the question. To answer your question, I did not go for any cost benefit analysis. I just wanted to suggest if the improvement have any potential. That's all I did for this research. I hope that answers the question.
Okay, great, thank you. Okay, super. Just checking, I don't see any more questions. We are going to conclude the Q&A section. Thank you everybody for submitting questions, and thank you to the students for answering them. We will move on now to the next section with Inez.
All right, thank you, Ondine. So we will move on to presenting the results of the winners of the first, second, and third place video posters. Again, these video posters were evaluated by members of the Stride Center's External Advisory Board, so we thank them very much for taking the time to go through all the 15 videos and evaluating them. All right, we have no fancy drum roll or nothing, but we certainly appreciate all your efforts. All the posters were pretty good, the videos. Winner of the third place is Akhilesh Shastri from the University of Florida. So congratulations. I guess I can do that. I don't know if that works. Well, there's no drum roll. So congratulations to you, Akhilesh.
Yeah, thank you very much, everyone. Thanks to the judges. Thanks for giving me this prize.
Sure, no problem. All right, moving forward to second place winner. Our second place winner this year is Becca Curiosis from Georgia Tech. Congratulations, Becca. I think this is your second time, right? I think you won last, yeah.
Yeah, exciting every time. Thank you so much to everybody.
I think somebody from Georgia Tech may be on. I think Mike Hunter or Dr. Mike Hunter or Dr. Carrie Watkins, who's your advisor. But anyways, congratulations again. Oh, there's Carrie. Hello.
Congrats, Becca. Good job.
Thank you.
Congratulations.
There you go. Great. Thank you so much for participating. All right. And moving on to our first place winner. We have Lucas Yu from Georgia Tech. So congratulations again.
Wow, thank you. Thank you. This is going to be really a surprise. Thank you so much.
You're welcome. And to Akhilesh, Becca, and Lucas, I will be contacting you via email for some paperwork, like we've done in the past.
Great job, Lucas.
Thank you, Dr. Hunter.
Congratulations all. Great job.
Okay, so now moving on to the People's Choice Award that you all voted for. And so let's give a big congratulations as well to Syed Anaf Morshed. So Syed, congratulations. And
thank you.
Syed, you are from, sorry,
FIU.
FIU, that's right. So congratulations.
Thank you.
We will be sending you a certificate in the mail, so I'll be contacting you as well. And that concludes our student poster showcase competition. Dr. Lilly, if you would like to say a couple of closing remarks.
Sure. Great job, everyone. I enjoyed the presentations. I think that this was a very nice format to have the 3-minute presentations. And so as we hopefully will be in person next year, perhaps we will do a combination of the two. But looking forward to seeing everyone hopefully soon in person. And thanks again for your great work. Appreciate it.
So I have one more comment that Ondine and I were commenting as we were working through this. This format actually gives everybody an opportunity to see everybody's work, because in a poster competition, you're going from place to place. You might not see everybody's work all at once. So it's just a difference, but it's a nice snapshot of what everybody's doing with Stride.
Silver
and
lining.
I'd like to thank Ondine for helping with organizing this event. She was very instrumental in this. So thank you, Ondine. All right.
Thanks, everyone. Have a great weekend.
Everyone.